KSH by default on Open.
There you go, sorry.
Because KSH is public domain, so we can include it in base. All right, so hello everybody. Welcome. I'm going to talk to you all about OpenBSD, which is something that's very near and dear to my heart. I have been an OpenBSD developer for a long time. It is beginning to make me feel old if I say how long I've had my developer account for. This fish is our lovely mascot, Puffy, the puffer fish. I will have a lot of artwork. One of the things that we like to do with all of our releases is make songs, original songs, and original artwork. So lots of these slides will be peppered with all of our artwork. So, has anyone here heard of OpenBSD before? Raise your hand. Cool, so we have a couple of people. Anyone ever send any patches to OpenBSD? Anyone else here have a developer account and is just secretly trolling me? Fair enough. Fair enough. So, I'm here to talk to you all about OpenBSD, kind of what we are, what we do, why we're potentially interesting to all of you, how it is that we help drive the security world forward, and kind of what lessons can we learn from all the work that we've been doing since late 1995. In full disclosure, I didn't get there till 2013, so I haven't been quite there since the start, but I've been around for a while. So if you go to our website, openbsd.org, it will tell you that it is a free, multi-platform, 4.4 BSD-based Unix-like operating system. Our efforts emphasize portability, standardization, correctness, proactive security, and integrated cryptography. As an example of the effect OpenBSD has, the popular OpenSSH software comes from OpenBSD, and we all use SSH. It's kind of one of those core utilities that forms the backbone of the internet, along with TCP/IP, another BSD invention, although that was 4.4 or 4.3 BSD back when it was still at Cal Berkeley. So lots of things that underpin the modern internet actually do come from these family of operating systems. But that's like a technical explanation that is like technically true, but also doesn't tell you a whole lot. So what really is OpenBSD, and why have I decided to be hanging around it for as long as I have? So yes, it's an operating system. You can install it on your computers, and you can run it just like you'd run Windows or Linux or anything else. But we are a lot more than that. You know, we are a developer community. We do kind of prioritize developers and our interest in moving the operating system forward. But we, of course, are also a user community, right? There is no operating system that lives without a bunch of users. And we certainly have a bunch of users, right? Every operating system these days lives with a user community as well. We are also artists and musicians, like not kidding. Every single release, we come out with original artwork, and most, but not all, come out with original music. And you can even go to openbsd.org/lyrics.html and download that music. When I was in graduate school here at RPI, I had a friend in the CS department. He was another graduate student. And he tells me once that when he was in high school, he was throwing a party for his friends, and he knew he should play music at the party, and he didn't know what music to play, so he downloaded a bunch of OpenBSD release songs and played them at his party. And I'm sure his party was a huge hit with all that great OpenBSD music. I mean, it's kind of catchy. I don't know if I'd play it at a party, though. We're also people who care deeply about security, right? People oftentimes do think about and credit OpenBSD as one of, if not the most secure OS out there, and has been doing this for such a long time. I think it's still on our website on the homepage. It says like two remote holes in the default install for a heck of a long time. Right? We look at things like that as something to be proud of, right? You install OpenBSD, you know that unless, I guess, you screw it up, you'll be okay. We'll take care of the hard parts, and then you can build whatever it is you want to build on top of those hard parts that we already took care of. Of course, it is globally critical software, right? You can't get by today without using SSH, and as we will soon see, a whole lot of other technologies that come out of OpenBSD that you might not be aware of, or you might know about them but not know where they come from. Which ultimately leads to, we're a whole bunch of people that you and the security world and the internet and everyone ultimately relies on. We're not the only ones that you rely on. It'd be kind of cool if we were. But right, we are part of the people that you rely on to get your work done, whatever work that is that you want to get done. All right, so quick agenda for this. We'll talk a little bit about the history of OpenBSD, just real quick. We'll talk about innovations. We'll talk about how we pioneer different security features. We'll kind of walk through a bunch of different security features. We'll talk about how we push the world forward. Like, it's one thing to create interesting security features, but the real power in them comes with the ability to make the world change and be better as a result of adopting our innovations. We'll also talk a little bit about how to get started, how to get installed on your machine if you are interested in running OpenBSD. I think it's cool. I run it on all of my machines and have for like 15 years at this point. So you definitely can have a normal computing life on OpenBSD. And then we'll kind of wrap up with a conclusion. All right, so who am I? I kind of didn't introduce myself at first, although I'm sure you saw the slide deck. It kind of gives away who I am. So I'm an OpenBSD developer. I'm one of those fancy, cool people who actually has an openbsd.org email address. My username is bcalla, B-C-A-L-L-A-H. So if you're ever looking through the commit logs and you see that name, that is me. I got my account, if I remember correctly, it was something like January 7th, 2013. So it's been quite a long time. My priorities have mostly focused on porting third-party software, making sure that third-party software is better than I found it, and then also running correctly on OpenBSD, which if your code runs on our operating system, you probably engineered it well. Our operating system is designed to be a hostile environment for your code. It is designed to make your code fail hard and fail fast, to make sure that you build it better next time. But I've also done some other things as well. I built the official Octeon release binaries a couple times, like way back, I think in like the 5 series. So if any of you actually bought some of those old DVD releases that we used to make in like the 5.4, 5.5 era, and you look through the booklet, you'll actually see my name in there as one of the people who built the official release binaries for one of our 64-bit MIPS platforms, Octeon. These are my commit logs as of February 29th. So I've been doing this a long time. I'm almost at 2,500 commits. I'm probably there by now because this was from a few weeks ago. But as you can see, like, I enjoy this stuff. I have made a commit literally every single hour of the day, according to this, every day of the week, every month of the year. That gap in the middle there is, we'll call that graduate school. I did have to go to graduate school and get a degree and get a job. I know that's tough, but I had to go get a job and stuff like that. But I've been doing this for a long time. I clearly enjoy it. I've made a lot of really great friends along the way. I've gone to some really cool places and talked about a lot of really cool, and at least I think is really cool and interesting stuff. So let's talk a little bit about history, not a ton, but a little bit about history. And like I said, I'm going to pepper in all of our release artwork and stuff like that because I think it's cool. And a lot of people spend a lot of time working on this artwork, so let's show it off. 1995, October 14th, OpenBSD is founded as a fork of NetBSD. So for those of you who don't know, BSD comes from Cal Berkeley in the 70s. Other things that come from Cal Berkeley around that time are things like the VI text editor, which a lot of us still use today. I certainly still use today. It's okay. Some of us are going to use Vim until we are long gone, and if we could rise from the dead, we'll probably continue to use Vim and VI and other such editors. We get to the 90s, and we begin to see it become totally open sourced with the 4.4 net releases. FreeBSD and NetBSD kind of begin life coming out of that era and what we would call 386 BSD. And then that's about like 1993, 1994, 1995, late 95, OpenBSD forks off of NetBSD. A couple years later, Dragonfly BSD will fork off of FreeBSD as a result of disagreements in the SMP stack for FreeBSD, transitioning from FreeBSD 4 to FreeBSD 5. And those are really the 4 main branches of BSDs today: Free, Open, Net, and Dragonfly. This is what this looks like. This is the whole Unix family. We are here. So this one's us. So unlike Linux, which is here, OpenBSD, as do all the BSDs, actually do trace their lineage directly back to the original AT&T Unix that came out of Bell Labs in the late 60s and early 70s. So we can truly lay claim to having lineage to that original Unix operating system that came out of Bell Labs. Of course, it's a little circuitous and all, and at this point in time, there's a lot of sharing between a whole bunch of different operating systems, but we are part of that traditional Unix family, obviously on the BSD side of that family, as opposed to the System 5 side of the family. All right, so let's talk about innovations, because that's really what I think is most interesting to talk about when it comes to OpenBSD. What it is, what are we doing to further security, to make things better for everyday people, and how we think about making things better for everyday people. There are a ton of innovations. I could be here for a day talking to you about all the different innovations. So I can only highlight a few, so I will only highlight a few, but I'll try to highlight the big ones that are kind of worth sharing and talking about. We were the first free operating system to provide a complete IPsec stack all the way back in 1997. OpenBSD was the first operating system to provide a complete IPv6 stack all the way back in 1999. And I hear it's just a few more months or years until we've all moved to IPv6. We've only been waiting since 1999 to move the world to IPv6. I hear it's coming any day now. We popularized privilege separation, and this started with OpenSSH, but pretty much everything, every daemon written for OpenBSD these days follows privilege separation. We were the first operating system to enforce a stack protector by default all the way back in 2003. We were the first widely used operating system to enforce ASLR by default, again, all the way back in 2003. The first widely used operating system to enforce position-independent executables by default back in 2012. Nowadays, we've moved our attention to things like designing our major libraries and kernel to be able to relink themselves every time you reboot your machine. So if you have an attacker that is able to figure out where different rich pieces of memory are in your major libraries, you hit the reset button, and now they are in different places. So whatever attack, whatever script they just designed will no longer work. We are the place where SterilCat and SterilCopy come from, all the way back in 1998, which has finally, as of I think either this year or last year, probably last year, finally got adopted to be part of POSIX. Everyone's already using it, so it feels like it was a formality, but it has finally happened. And then other things, like thinking about how to protect yourself against different types of malloc bugs and computing mallocs incorrectly, things like realloc array, which solves the problem of what happens, does anyone know, if you call malloc and part of your call to malloc requires you to multiply two numbers together and they overflow. You're going to get whatever the result of that overflow is. It's probably not what you want. Right, so realloc array, well, for malloc and realloc, will actually compute if you would have an overflow and abort and not actually do the malloc if you were to have an overflow to protect you from accidentally basically mallocing an incorrect memory size and then shoving something into a piece of memory that doesn't actually fit in there. So some things I want to highlight, SterilCopy and SterilCat. Has anyone heard of these functions before? Has anyone used these functions before? Cool, so I see one person saying yes, he's my new best friend. As for the rest of you, we'll explain it. So here's a problem. Strings in C are hard. What is a string in C? Yeah, it's an array of characters, hopefully terminated by a null byte. Hopefully, on our best days, terminated by a null byte. That means you have lots of potential to get things wrong. And there's even more potential to corrupt memory. Right? So I teach a course at RPI called Modern Binary Exploitation. I basically teach students how to hack into computers. And things like buffer overflows and abusing strings is one of our favorite things to do. That and ROP chains, that's our other favorite thing to do. And we'll talk about anti-ROP chain mitigations in a bit. Right, because if you have corrupted memory, you have the ability to corrupt memory, you have the ability to overflow buffers, then that's a really big playground for your attackers, and kind of anything can go at that point. Does anyone know what the problem with the functions stir copy and stir cat are, and why it is we want to avoid them? Yeah, it just keeps on going. Right? They're unbounded copies, so it just keeps on going until it sees that null byte. If your buffer isn't big enough for whatever that is you're putting in that buffer, it doesn't care. It just keeps on writing the memory into that buffer. Right? Gets also has the same problem. Right? It just keeps on reading until it hits that null byte. And if you run out of space in your buffer, you will eventually go and write interesting things, like a return address, perhaps. And then if you can get that function to return and you can control where it goes, then you can have a whole lot of fun with that. So that's stir copy and stir cat, right? Unbounded, almost always bad. A fix was attempted, but it actually has a really fatal flaw to it. So the fix, I'll put in quotes, was stern copy and stern cat. Does anyone know what the fatal flaw of those two functions are? If you write into something that is exactly the same size of your buffer, you don't write a terminating null character. So you have to make sure you write the size -1 all the time, because if you write something that is exactly the size of the buffer, you don't get the terminating null. Because stern copy and stern cat, the way I always teach it to students in MBE, is despite the fact that they have str in their name, that's actually a misnomer. They're not string functions. They are buffer functions. They operate on every single byte in your buffer. Because if what you put into that buffer is smaller than the buffer size, the entire rest of the buffer gets filled with null bytes. So it's kind of a misnomer. It's actually operating on buffers as a whole, not really on strings, despite the fact that it has the str in its name. Right? So if you write into something that's exactly the size of the buffer, you won't get that terminating null byte, which means in theory, you could read out of it, and if there are no null bytes coming after that, you might read into a whole bunch of interesting memory that you can then learn something from and leverage an attack from. So in 1998, Theo and Todd Miller, Todd is also the guy who is the maintainer of sudo, for those of you who use sudo, came up with sterile copy and sterile cat. So both functions take 3 parameters: a destination buffer, a source buffer, and the size of your destination buffer. You actually do put in the size of your destination buffer as that 3rd parameter, because the function itself guarantees that you can only write at most buffer size -1 characters, guaranteeing that you will always have a null byte. And so it'll always put the null byte in. Now, of course, kind of the pin in that is assuming the developer knows what they are doing. Right? If the developer gets this wrong and they put in a buffer size that is larger than, buffer size that is larger than the actual destination buffer, weird things can happen. So I want to introduce you to a little bit of a philosophy that you may or may not agree with, but roll with us here. It is easier to teach developers to do the right thing, because there are fewer of them, than it is to teach users to do the right thing, because there are many of them, and they may or may not be technically inclined. So we are willing to kind of put the burden of security on the developers to actually understand their code, and to understand their code well enough that they do engineer it well. Like, yes, we will have mitigations in place for the developers who don't do that, but we do want to help bring up the whole developer community and teach them better ways of doing code as best we can. So hopefully, no more buffer overflows, right? So long as you get that size of the destination buffer correct. But you might be thinking, where is this used? And I did kind of spoil it that like POSIX has now finally incorporated it into the standard. But before that, like literally everyone was just copying and pasting the code out of the OpenBSD repository. Linux is using it. Pretty much everyone is using it. It's kind of hard to like name off the list because it's basically name me a piece of software written in C and they're probably using it. But the good news is now that it's finally in POSIX, all the POSIX compliant C libraries have to have an implementation of it. So like your glibcs now will have an implementation of it. They resisted since 1998. They refused to put it in. Now they have no choice. And now it is actually in glibc because they have to follow the standard. Standard says that you need it. They, of course, in classic GNU fashion, rewrote it. So internally, it looks different than ours, but whatever. It functions the same way. And that's the important bit. As long as it functions the same way, that's the important bit. So you shouldn't have to copy and paste surlcopy and surlcat anymore. Any compliant libc, compliant to POSIX, will have these functions, and you can just use them and make your life a little bit easier when it comes to dealing with strings. What I think is really cool is the anti-ROP chain mitigations. This is stuff that I love. I spent a whole week in my MBE course talking about this stuff because I find this stuff so interesting. So who here is familiar with ROP chains or return-oriented programming? A couple people. All right, so for those of you who don't know what it is, either of you two with your hands up want to explain it for us? It's okay, I'm putting you on the spot. It's totally, I'm a professor. I'm used to doing it to students. I cold called her in class the other day and then felt totally guilty about it because another student totally just like gave it to me for doing that, but it is what it is. So return-oriented programming is the idea that you can take instructions, particularly in x86 64. One of the really interesting features is that instructions start wherever you say they do, not actually at the beginning of instructions, because they have unaligned access. So you can literally drop the pin anywhere in your code, and the CPU will on the fly just reinterpret those instructions based on your starting point. You can put addresses into buffer space that you control that effectively jump to other instructions that always end in a return, which brings you back to your stack. If you fill your stack with these addresses that always have functions that end in return, and the code before those returns do interesting things, you literally are writing code and exploit code and malware basically with the code that is already existing on your machine. You are just calling into your library, taking this tiny little snippet that does one little thing, returning back to your stack, and your stack is just going to jump to the next address where you do another tiny little instruction, return to go back to your stack, and so on and so forth. And usually you'll end with some gadget, they call them gadgets, some gadget that ends like with a syscall or something. You probably get a shell. That's what a lot of people want to get. That's what we get in MBE. So how do we actually defeat code like that? Like, how do we actually defeat attacks like that? One thing that is really very, very interesting is your registers on your x64 machines are actually conspiring against you. So this is a commit made back in, I guess, 2017, 2018-ish. I quoted the important bit. The compiler is generally free to allocate general purpose registers in whatever order it chooses. So we use Clang by default. If you install OpenBSD, you will get Clang. It is part of the base install, mostly due to licensing reasons. The way Clang orders their registers is like this. And I've highlighted both RBX and EBX on purpose. Particularly with the 32-bit ones, right? EBX is kind of in the middle of the list. RBX is a little bit further along in the 64-bit registers. But the 32-bit register is actually pretty high up. Does anyone know what happens if you have instructions where your source register is A and your destination register is B, or you have single register instructions that use B? Does anyone know what hex codes these translate to? or importantly, which one they end with. Does anyone know what hex digit this ends with? That's the important bit.
Null's a good guess.
Null's a great guess. It's wrong, but it's a great guess. So does anyone know what byte x86-64 uses for the return instruction? It's 1 byte. Anyone know what that byte is? It is C3. It turns out if you have instructions where your source register is A and your destination register is B, that B register will become a C3 byte. Now, in the context of dropping the pin at the beginning of the instruction, you will in fact have move A to B or add A to B. But what happens if you drop the pin on 89? Well, the CPU is going to reinterpret whatever 89 C3 is. And it probably is something that ends in a return. This one down here is kind of a better example. So if you jump by, 11 bytes, JE0XB, and then you increment B, you end up with 7409FFC3. If you ignore the 74 and drop the pin on 09, that gets reinterpreted as the 2 instructions, or EDI, followed by a return, which means you can mine through your code for all of these C3 bytes and just kind of walk back the pin every single byte until you find interesting instructions that you could chain together to make ROP chain attacks possible. Now, or EDI might not be the best instruction to use for an attack, but let's say you want to increment your A register because you're going to make a syscall, and you find an instruction that's increment A or add 1 to A, semicolon return. You can just chain a whole bunch of those together until you hit whatever syscall exec VE is, and then if you find a syscall, you can then just run exec VE. Now, hopefully you'll also populate RSI and RDI with something interesting like a shell, right? But that's how you would construct these kinds of attacks. You would find all these C3 bytes, and they're not just returns. They happen other times as well. Just move that pin until you get interesting sequences of instructions, and then chain them together, usually after you've found some buffer that you can just exploit. So how do we avoid this? Anyone want to take any shots at how we might avoid generating these C3 bytes where we don't want them? Because obviously return instructions will still have to be a C3. But how can we avoid these other C3s that come about for other reasons, like adding where your source is A and destination is B? Anyone want to take a guess? Where are my good assembly programmers? I found the wrong crowd for assembly programmers. 30 years ago, maybe.
I learned assembly on a back.
All right, so what if, as a starting point, we just moved to the BX register, right? We said the compiler is generally free to allocate general purpose registers in whatever order it chooses, and we know that that's what Clang wants to do. What if we said we don't care what Clang wants to do and just shove all those B registers all the way at the end? And that's exactly what we did, and that's the diff. It's not all that long, right? You can take your B register and shove it all the way at the end. These two should be at the end. These are your stack pointer registers. And then where else did we move B? Where's the other one? Yeah, we moved it down here. Again, these are going to be your stack registers, so they can stay behind those. So what if you just put the B register at the very, very end? And that way, your instruction selector has to go through every other existing register before it gets to B. And while I know more modern x64 chips added a bunch of new registers because 16 is actually not as many as you think, it is better than the 8 that you got in x86, but still not great. But kind of at the base level, we're still working with only these 16 registers. So that buys you more time, right? It buys you more registers to churn through before you have to use a B register. If you do this, this costs you basically nothing because all registers are going to work at the same speed anyway, right? There's no priority in register speed. Just that one change alone, which ends up being what? 6 lines of change, right? Plus 3, minus 3, not a whole lot. Removed about 4,500 unique gadgets from the OpenBSD kernel, representing about 6% of all unique gadgets that lived in the kernel. Now, is that 100%? No, but anytime you can reduce your attack surface, that's probably a good thing. And for a change that costs almost nothing, I say roughly zero cost. One of my graduate students actually discovered that occasionally Clang will rewrite instructions to be a little bit longer because it can't find the B register, but they're very, very few and far between, and we're talking about like an addition of like maybe 100 or 200 bytes over like a several megabyte program. So we're not talking about like a huge code size increase here. So for roughly zero cost, you can have a significantly reduced attack surface, right? And that's just the kernel. Think about things like Chrome, Firefox, LibreOffice, right? All these gigantic programs that are coded in C++, or really anything that ultimately uses either GCC or LLVM for its backends, right? So for basically nothing, you can reduce your attack surface for every single program that eventually gets compiled through, well, in this case, LLVM. You can do it on GCC too. I am trying to get a graduate student to do it on GCC. We'll see how that goes. However, there are cases where you do actually need to use the B register. What you can do in that case, for any of you who've actually coded in either LLVM or GCC, LLVM is actually really nice in terms of adding optimization passes. You just basically write a separate code module and just link it into the list of optimization passes. GCC is a bit harder to do in terms of optimization passes. But you can write an optimization pass that will scan through all of your code and notice when you have output or are going to output one of those bad instructions, and just rewrite it to not output those bad sequences of bytes. So if you ever have something where your source is A and your destination is B, you can simply exchange A and B, and then do your operation where B is the source and A is the destination, and then you get D8 bytes that don't do anything, and then exchange them back. Now you might say, well, that's going to add 6 bytes. And that's true, it does add 6 bytes. But remember, we've pushed the B register all the way to the back. So you are far less likely to encounter having to rewrite these instructions than you were before. And exchange is one of the fastest instructions that you have available to you because it's all register to register. There's no memory access or anything like that. So it's super quick. So it's a pretty negligible performance and size cost. It ended up adding 0.15% of a size increase to the OpenBSD kernel. But it knocked out an additional 3,700 gadgets, so an additional 5% of all unique gadgets from the kernel. And that's just teaching your compiler to output what I guess we would call better code in those situations, to give your attackers fewer of those C3 bytes that they can go play with and come up with their own gadgets and then use against you. And 11% from just those 2 tiny changes ain't so bad. At least I don't think it's so bad. I think that's pretty good. So that's one solution that you can have, or one part of the solution you can have for helping to eliminate ROP-oriented attacks. Another one we call RetGuard, and both of these mitigations, you might have noticed, I mentioned Todd Mortimer. He wrote a paper on this. He's the guy that actually came up with these strategies and solutions, so all credit goes to him. So raise your hand if you are familiar with stack cookies or stack canaries. All right, same 2 people. Either of you want to explain it to us?
Yeah, sure. So your stack is going to have some set of expected values, and before or when you return to the stack, those values are going to be checked to make sure that they're there, so that like something unexpected hasn't been written to your stack. That's going to
Yeah. So traditionally, yeah, exactly. So traditionally on x64 machines, a stack frame begins with whatever address you return to when you hit return, followed by whatever your base pointer should be from your previous stack frame, so you know where your base pointer goes back to, and then that stack cookie, and then your local variables. This is usually the way GCC is going to write that out. Does anyone know what like the traditional flaw in GCC's implementation of stack cookies are. And you're going to learn about this real soon, and it's going to be very important knowledge for you, so pay attention. Anyone know what the flaw is? So the flaw is GCC will use the same stack cookie for every function. So if you are able to leak the stack cookie in one function, you already know it is the stack cookie for the other functions. And so you can leak it from one function, exploit a different function, and be able to rewrite the cookie in its place en route to rewriting the return address for that particular function. So that is the traditional flaw in GCC's implementation. What if instead every function could have its own stack cookie, and that stack cookie could be meaningful? The other interesting bit about GCC stack cookies is because they're all the same, the only thing you verify when you check the stack cookie is that the stack cookie is the stack cookie, which like sounds obvious, but it has no relation to any other code that exists. What if we found a way to give our stack cookies a relationship to other code and other things on our stack that exist? So you can do things like compute a random cookie and XOR it with the return address of that function, because you already know it, because you already pushed it onto the stack. You could then store that result as your cookie. When you return from the function, you can compute the value that you have on the stack and XOR it with the return address. And you should get back that original random value. Now, one of the nice things about OpenBSD executables is you get a whole bunch of like randomly assigned values in the executable automatically on program startup. So every executable already has a bunch of entropy and random digits it can just pull from to do stuff like this. So you compare that XOR to the random cookie. If the comparison passes, then you must have the right stack cookie and you continue. If it fails, just as usual, you abort. Traditionally in GCC, they actually have a separate like abort function that they call. We actually just use an int3 sled, right, which is your CC byte, which is your debug break, which will cause an abort trap on your runtime. So every single function, if you look through it with like a disassembler, you will see before every actual return, before every actual C3 byte that you need, there'll just be a laundry list of just CC over and over again. Does two things. One, it means if you try to jump to the return address, you are not going to make any interesting gadgets. You're just going to hit breakpoints and abort. I guess you can use the C3 all by itself, but you only get a return, and therefore like it doesn't actually do any work. The other thing that you get is that you know your return address is the one you actually want to return to. You verified your return address as well through this mechanism. So the effects of this. Performance cost was a little bit less than 2% at runtime, right? Unfortunately, as we all know from security, sometimes you got to trade off performance for security or size for security, right? There's always, unfortunately, a bit of a trade-off. Code size, it does cost about 31 bytes per function to do this, which did grow the OpenBSD kernel by about 7. 70 would be bad, 7 is okay. 7% kernel size increase, but it removed literally half of all gadgets from the kernel, which represented about 20% of all unique gadgets. And you get a better stack protector, because now you are actually verifying that the address you are going to return to is actually the address that you want to return to. So that's on x64, where you have that unaligned access, where you can drop the pin anywhere in your code sequence, and the CPU will just reinterpret that sequence of instructions. On ARM, you get to choose whether or not you have aligned or unaligned access. Linux, for performance reasons, chooses unaligned access. So they have the same problems that x64 does. We default to aligned access, which means every single instruction has to start on a byte boundary. It's a 4-byte boundary, I think, for the ARM chips. That means you can't have these kinds of gadgets about dropping the pins in unique locations, or what we would call a polymorphic gadget. That's like the technical term for that dropping the pin thing, a polymorphic gadget. So if you have strict alignment, you can't have polymorphic gadgets because you have to start your instructions on that 4, 8, whatever it is, byte boundary. So on ARM, before RetGuard, we had about 70,000 gadgets in the, I think it was the ARM64 kernel. And after RetGuard, we had 46. And I'm pretty sure all 46 were in handwritten assembly code as part of the bootloader. But all the C code no longer had any gadgets whatsoever. I mean, that's a pretty huge reduction. And yes, people who are smarter than me went back and fixed up those bootloader things. So I'm pretty sure we have like 0 or like almost 0 gadgets in the ARM64 kernel, which is pretty great. Because if people want to do ROP attacks against you and they don't have any gadgets, they can't do ROP attacks against you. I think that's pretty cool. The other interesting thing is, right, so this is built into our modified version of Clang, right? If you install OpenBSD, all this stuff happens by default. Pretty much on every user-land program, right, because they do kind of vary, you're looking at a reduction of anywhere between 25 and 35% of all gadgets from these mitigation techniques. Again, better on ARM than on x64, so that 25 to 35 is on x64. Better on ARM because of that aligned access, of course. All right, so some other things I want to talk to you all about. Pledge. So Pledge is really interesting in the sense that it solves a problem that most developers don't even know that they have. And the problem is, do you actually need to be able to make any random system call at any random point in time? And the answer for the vast majority of programs out there is no. Right? If you have a program that all it does is like take in some sort of input from a user and displays that information back to the user, do you need to be able to fork an exec in that program? Assuming it's like single-threaded, I get it. Assuming that you're not trying to do things like that, right? But normally, no, you don't need to do things like that. However, if your program can simply call any random syscall, if attacker can wrest control of a buffer and put in some sort of either shellcode or ROP sequence, etc., that then calls that syscall, that program will happily call that syscall. So Pledge answers that problem. Pledge reduces the number of syscalls that any particular program has access to. Again, this is on the, we are teaching the developers to understand their code better and write their code better. Right, so on x64, for example, syscalls are identified by a number you put in the A register right before you make your syscall. So like 3, for example, is read, 4 is write. There's like a few hundred of them. I don't remember them all off the top of my head. I know 1, I think, is exit, so I got that one down. For Linux x86, or sorry, Linux x64, hex 3b is exec VE, because I teach it every year. So that's what I've committed to memory. Right, so you have at least one syscall you don't want attackers calling, exec VE. There are others too that you probably don't want attackers calling. Unfortunately, you can't disable syscalls entirely. If you're like, hey program, you can never make a syscall, your programs can't do all that much. They can basically just operate on shared memory given to it by another process, and it literally can't even exit because exit is a syscall. So, right, you just have this like floating process from then on. So you do need some syscalls, at least one. You need to be able to exit effectively. However, what if we could group syscalls by function and make a new syscall that could accept a list of those groupings and then restrict a process to only being able to call the syscalls in those groupings? And that is what Pledge is. So Pledge just takes a string, and that string is a space-separated list of whatever families of syscalls you want to have. There are other things out there that do this a little bit differently. I think in the Linux world, I think it's SE Linux or it's PAX, it's one of them. They literally have like on-off every single syscall that exists. And you have to like go look for every single syscall and turn them on and off, which can be error-prone, right? Still good, still better than nothing, but can be error prone. This helps reduce the cognitive load of your developers while still trying to give maximum benefit. So some common syscall groups include things like standard IO, which gives you all your standard IO, RPath, which lets you read from the file system, WPath, you could write to the file system, CPath, you can create new things in the file system, INET gives you internet, proc gives you fork, exec gives you exec, right? There's a bunch more of these, but these are kind of some of the common ones. So you can say like pledge, and then your string could be standard IO, RPath, WPath, meaning I have a program that's going to blast something to my console, it can read stuff from my file system, and it can write stuff to my file system. But that's it. It can't do anything else than that. You can call pledge multiple times in a program. The caveat is subsequent calls to pledge can only make it more restrictive. So you can't add syscalls back once you've taken them away. You can take more things away, but you can't add things back. And this is possible to do. We have pledged Chrome and Firefox. So it is possible to get really huge, complex programs, understand what syscalls they are actually using, and restrict them to just those syscalls, right? And browsers are like an obvious thing you want to protect against because they're huge, and it feels like every couple of hours is a new exploit making the news about one or both of them. All right, so let's talk a little bit about pushing the world forward. So 64-bit time T. What happens at 3:14:07 UTC on 19 January 2038, which is not as far away as it sounds? What happens at that exact moment? Yes, overflow of what? Overflow of 32-bit time T, right? So time T originally in Unix, originally time was, I think it was a 1/60th of a second, and it overflowed every couple days. And then they got smarter, like, what if we only made it tick once a second? But they made it a signed integer. So that's the point in time where it will overflow, and we'll all go back to the past. Unless we change what the type of time T is to something that's 64-bit, which is what we did. We actually weren't the first ones to do it. I think NetBSD beat us to the punch. However, we were the first ones to then go through our list of third-party packages and give everyone else patches so that they would be able to support 64-bit time T when everyone else caught up to us. It's like one of the early things that I did when I first got my account in OpenBSD. This is one of the early things that ended up happening. So there are still some operating systems that have not yet caught up to 64-bit time T. But once they do, none of the software that you use on them will break. We've already solved that problem. And we solved it about 10 years ago. So that's a problem that's already solved. It's a problem that you might not even know that you have or will have in a couple of years. But we have already solved it. And it took a lot of work and a lot of time, but we did eventually solve it. So now, right, pretty much any program you can think of can support 64-bit time T. Something that we're kind of working on right now is BTI and IBT, indirect branch tracking. So on both x64 and ARM64, there's a new feature on most new chips that an indirect branch or a function pointer can only pass control to a new location if that new location begins on x64 an NBR64 instruction or on ARM64 a BTIC instruction. The nice thing about the x86 one, x86-64 one, is NBR64 decodes to a weird NOP on CPUs that don't support it. So if you don't support it, nothing happens. But if you do support it, you get that indirect branch tracking. This is the FCF protection branch flag on Clang, which we now enable by default. You'd be surprised how many programs do indirect branching and immediately crash because they jumped somewhere that was not protected or they didn't expect or something like that. So we have gone through and helped fix the world so that when every other operating system decides to put FCF protection branch as their default compiler flag, all the software will just work. We've already solved the problem. It's mostly already fixed by now, the couple stragglers that are left, and admittedly, I'm one of the people who has left to fix one of the stragglers. I just have to find time to do it. But then you all benefit. We suffered the pain so that none of the rest of you have to worry about that. So how do we get started? The good news is there are installers. They're both USB installers and CD/DVD installers that you can just go to our website and download. We call x86 64 AMD 64. It's a weird BSD kind of terminology holdover. We name our platforms after the first CPU that had that instruction set, and AMD 64 beat Intel to the punch for 64-bit instructions, so we call it AMD 64 even to this day. But they will work on your 64-bit Intel machines. Yeah, AMD and Intel have a mutually assured destruction pact because Intel owns the 16 and 32-bit instructions, and AMD owns the 64-bit instructions. That is a true story. So this works great on VirtualBox, or like your, maybe not this, probably this one, but like your laptops too. Installation is just like a shell script. You could just hold the enter button down and wait 5 minutes and you'll have OpenBSD installed. It's great. The only thing to answer is if you want to put in your username. And the trick about putting in your username, it will ask, do you want to put in a user? And if you type in the word yes, it'll say, no, really, what's the name of your user? So it actually does want you to put in the username at that point. There's tons of different third-party things. We use something called PackageAdd, which is homegrown to us for our third-party packages. What you get on OpenBSD, and this is true of all the BSDs, you get enough in the default install that you can immediately begin to be productive in making software. C and C++, for us, Perl, awk as well. Tmux, for those of you who don't use Tmux, you should be using Tmux. It's the best piece of software on the planet, particularly for those of you who are in your terminal all day long. The person who writes Tmux is an OpenBSD developer, comes by default in base. You get all of the standard Unix utilities. We still ship a bunch of video games from the 70s that are like back from like the original BSD. You get VI, which is great for me. You get an Emacs clone called MG. You of course get ED. You get 2 window managers and XOR. You get a tiled window manager and a traditional floating window manager, and of course the ability to download third-party packages. All right, so let's wrap it up because I've been talking for like 45 minutes already. So I think OpenBSD is really interesting because it is an active, vibrant community that has the power to push the world forward, and we use that power for good in order to make everyone else more secure. That list of security innovations is just going to keep growing as the years keep going on, and I mean, honestly, the truth, the reason I've been hanging around it for as long as I have been is it's just fun. And when was the last time you heard the word fun and operating system in the same sentence that didn't include the word not in it? So I think it's fun, and that's what keeps me hanging out in the community and doing all this interesting stuff. So that's it. That's about 45 minutes. I don't want to take any more time than that. That's me. I'm kind of like everywhere. I'm on Mastodon. You can, of course, always email me. I got a website. I got a LinkedIn. I live in the area. I'm a professor at RPI, so just come find me. I'm not hard to find. I'm always happy to talk about this stuff. This is stuff that I really enjoy. This is the stuff that got me interested in security. And the community that I got here is what made me interested in this stuff. So hopefully, I've shared a little bit of that interest, and thank you for coming and hanging out with me.